In the last video, we showed how to get the work to go from one position to another position due to a force F, where the force in this case was constant. And we showed that it's the dot product between the force and the displacement vector from the first position to the last position. In this case, the mass is going in a straight line path. So the question we could ask then, what if the force was not constant? What if the magnitude and direction or direction of the force was changing during the motion for a straight line path? Or even what if the path is not a straight line? What if it's a curved path? So how would you define the work in that case? How would you get the work? If the path is straight and the force is changing value, magnitude or angle as the mass goes from this position to this position, as usual with any kind of case where we have a long path, you can always cut it up into small parts. And the same thing happens if you go on a path. What if you have, for instance, like a roller coaster or some kind of car that's moving on some curved path like this? So it starts out at an initial position and it ends up at a final position. And you ask the question, what's the work done by gravity as this car or this mass goes from here all the way to here? So the way we think about it is we can cut up our path into small intervals, small parts. And of course we should let the number of parts go to infinity, but I'm just showing you here a few of the parts. So the vector, the force vector, is the same everywhere, unless of course the altitude is changing by a huge amount, because g at the surface of the earth, g is 9.8 meters per second squared, but if you go to very high elevations, the g is not constant, it changes. So in general, g for this problem, it's constant, but it could change. And we can deal with forces that change magnitude as well as change in the having a curved path. So this will allow us to deal with any case, whether the force changes or not. So the way we do it, we cut up the path into small elements of length, delta R1, delta R2, delta R3, and so on. For each one of these elements of length, we can calculate what the work is. We can get the dot product between the force and the element of length. So we get a number. And then we add up all these numbers for all the elements of length, and that'll give us the total work for the whole path. So for the parts of the path, these parts, the angle is less than 90 degrees between the force and the displacement vector. So the work gives positive contributions to the work. And here, for these parts, the delta R and the force, the angle is bigger than 90 degrees, so you get negative contribution to the work. And then the total work will be the sum of all these. So roughly, just for these particular 7 elements, of course we said we're not going to have 7 elements, they have to go to infinity, but for these 7 elements, the work could be defined to be the force dotted into delta R1 plus the force dotted into delta R2 and so on, which you can write as in a summation notation like this. But of course, we should, to define the work accurately, we need to let the element of length go to 0. And so we have to sum the force dotted into the elements of length, and the elements of length point from A to B. And this would then give you the exact value of the work, or the exact quantity of the work. And you can write this then as an integral from A to B of the force dotted into dr. So in general, what if you now have any kind of force? It doesn't have to be gravity, it could be any kind of force, and you have some path. And you start from point 1 and you end at point 2, and you want to go along this path and calculate the work done by this force as you go along the path. So the definition then of the work to go from 1 to 2 due to the force F, you cut up the path into small elements of length. You get the force dotted into the element of length for each element of length. And remember, the force doesn't have to be the same value everywhere. It could be small here, it could be larger here, it could change direction. So this force vector doesn't have to be a constant, it could be varying. So you get the dot product for each element of length, which gives you a number. This gives you a number, this gives you a number, this gives you a number, and then you add all these numbers up. So in the end you arrive at one single number. And you can always write the limit of sums as an integral. And this is the way you would get the work to go from point 1 to point 2. But if you want to go from 2 to 1, then in this case the elements of length reverse. They go from 2 to 1. They point in the opposite direction, and you write the integral as integration from 1 to 2 f dot dr. Now, it's good to review the part that we did when we talked about this in the chapter on potential of the line integral to better understand this issue of going from 1 to 2 or 2 to 1. It was done in detail, explained in detail. So this is an example, the final conclusion of this part. If you want to get the work to go from 1 to 2, point 1 to point 2, this is how you would get it. This is the work to go from point 2 to point 1. And this, again, review the video we did on the line integral in the part on potential versus electric field, because this issue I don't want to repeat again. How you keep this dr always the same. It's always equal to dxi dyj dzk plus dzk. You never change this, and the reversal in the sign will come from the reversal of the limits. So here you're going from 1 to 2, here you go from 2 to 1. This is where you're going to get a difference in sign when you look at it from the integral point of view. When you look at it from the limit of sums point of view, you have to reverse the direction of the delta r vectors. In this case, they go from 1 to 2, in this case, they go from 2 to 1.